In this video, we're going to look at power series and functions. We're going to identify a power series. We're going to determine the radius of convergence and actually what it means. We're going to find the interval of convergence and what that means. And then we're going to use a power series to represent a function. So basically, a power series is just a geometric series in which my r for my geometric series is a variable. So if we remember, from I is equal to 1 to n, of a sub 1 r raised to the n minus 1. A power series is going to be something similar, except for now I'm going to have I equals 0. We usually start with 0 on the power series of n. Some coefficient, and then my r happens to be x raised to the n. And we don't do n minus 1 because we start at 0, just like we can take our geometric series and start it at 0 and say I equals 0 to n of a sub 1 raised to the r raised to the n. So our power series is basically a geometric series, but with r being replaced with a variable. Typically we use x, but we could use more than one variable, or we could use something other than x. We could use y. And just as a reminder of what it means to be convergent, so if the series is partial sums add up to that tend toward a limit, in other words, it tends toward a number, then we say it converges. If it doesn't tend toward a number as we add each one of the additional numbers, if it doesn't have a trending toward a number, say it trends toward infinity or negative infinity, then we say it's divergent. So here's some examples of power series where I say c sub n is my coefficient, x raised to the n, so I have basically the constant. So here's an example, more concrete example. So my constant, and then x raised to the 1, x raised to the 2, x raised to the whatever. Here my coefficients are all 1, but that's not always true. We say that, as you remember from a geometric series, if my ratio is less than 1, it's going to converge. If my ratio is greater than or equal to 1, it's going to diverge. My ratio now is x. So here's some definitions of what a power series is. Here's a power series in which I have c sub n, those are my coefficients, and my x is raised to the different powers, starting with 0, 1, 2, 3 on up. If my power series is centered at 0, and I'll explain what centered is in a moment, but if it's centered at 0, it's going to look like this. If it's centered at some other number other than 0, it's going to be x minus a raised to the n, still on my coefficient, still n equals 0 to infinity. As an example of being centered at 0 and centered at another number, this example and this example, because I don't see x minus some number raised to the n on either one of these, then I know that those are centered at 0. My coefficients would be n factorial. So here's 0 factorial as a coefficient, 1 factorial, 2 factorial, 3 factorial. So here's a more concrete example of what a coefficient could be other than 1. Here's an example in which the coefficient is 1 over n factorial. X to the n is the x to the 0, x to the 1, squared, cubed, and etc. Here's an example in which I'm not centered at 0. Notice I have x minus some number raised to the n. My coefficient is 1 over n plus 1 raised times 3 raised to the n. All of these are coefficients because these are going to be constant numbers. So the coefficient, I end up with 1, and then the coefficient of 1 over 2 times 3, 1 over 3 times 3 squared, and etc. Now we're going to explain what it means to be centered a little bit more by starting out with some theorems and more definitions. So we're going to consider this power series in which I'm centered at a. A can take on any real number. The series converges to a and diverges for all x not equal to a. The series converges for all real numbers x. And there exists a number r, which is larger than 0, so it's some real number larger than 0, so not 0 or negative, such that the series converges around this r. The absolute value of x minus a is less than r, and it diverges when x minus a absolute value is greater than r. And the values of x for when I'm looking at the endpoints, of my, we're going to call this a radius of convergence in a minute. At the endpoints, they may or may not converge, so I have to check the endpoints. So this is the definition. So we're going to have this power series. And wherever I have my radius or my center, which is at A, and it can be 0, then I'm going to have some distance in this direction in which it diverges and some distance here in the direction that it diverges. If my A happens to be any number, but my R happens to be 0. So here's an example when R is equal to 0. So it converges only at A. That's what it's saying here, only at A. Our other example is when my radius of convergence is infinity. That's this one. That means it converges all the time, everywhere, and not just at my center. My last one is this one, in which my R is greater than 0. So here is when R is greater than 0, but is a number, not infinity. So I converge in this interval where I have A, that's my center, plus R, that's going to be this edge, and then A minus R, that's going to be this edge. And then it's going to diverge on the outside tails. We don't know what's happening at the R minus A, or the A minus R and the A plus R until I check it. So I don't know if it's going to converge or diverge on those edges, and we'll find out how to check that in a moment. This is referencing what up above. So all of this is referencing what we just talked about. Now let's determine if these statements are true or false. For this first statement, that my summation of n equals 1 to infinity of a sub n, x to the n, converges at x is equal to 0 for any real number a sub n. So we have to determine if this is true or false. Well, we have the summation of n equals 1 to infinity of a sub n. My x gets replaced with 0. A sub 1 times 0 to the 1 plus a sub 2 times 0 to the 2 plus dot, 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 dot. And we can see that this is going to be 0. So no matter what I choose for a sub n, this will converge to 0. So this one is true. Let's look at our second true and false. If we have this series, which from n equals 1 to infinity of a sub n, x to the n, has a radius of convergence greater than 0, and if the absolute value of the coefficient b sub n is less than or equal to the absolute value of the coefficient of a sub n for all n, then the radius of convergence for the second series, n equals 1 to infinity of b sub n, x to the n, is greater than or equal to r. If we look at our first series, we know my center is at x is equal to 0, just by the structure. That tells me my radius of convergence for x must be in the interval between a minus r, so negative r, because a is 0, to r. Since my coefficients on my second series is less than the coefficients on the first series, then I know that if a sub n, x raised to the n, that series converges, that means b sub n, x to the n, also has to converge, and it's going to converge in the same interval, at least the same interval, if not larger. So we think about this when we first learned the comparison test or the limit comparison test or any of the ratio tests or anything that we learned in our previous chapter, that if the one above it converges, so must the one below it. Because my coefficients are smaller on my second series, and my first series converges, that means my second series will converge. So this is true. Now let's actually start to calculate the radius of convergence. Here's our next theorem. Let my series from n equals 1 to infinity of a sub n be a series with non-zero terms. let rho equal the limit as n goes to infinity of a sub n plus 1 over a sub n. If my rho is between 0 and 1, then it's going to converge absolutely. If rho is greater than or equal to 1, then rho is equal to infinity and it diverges. And if rho equals to 1, this doesn't provide any information. We got this from our chapter 5. We're going to combine this theorem with this definition. So let's find the radius of convergence for each one of these series. And the way that we're going to do this is by looking at the limit. So, the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is going to be equal to the limit as n goes to infinity of, everywhere I see an n, I'm going to replace it with a sub n plus 1, so a sub n plus 1 times 2 raised to the n plus 1 multiplied by x raised to the n plus 1 all over a sub n, 2 to the n, x to the n. Now remember, a to the m plus n must have started out with a to the m times a to the n. Normally we go in this direction, but now we're going to break this apart. So this is going to be the limit as n goes to infinity of a sub n plus 1, 2 to the n times 2, x to the n times x, over a to the n, 2 to the n, x to the n. We can see that 2 to the n's are going to cancel, x to the n's are going to cancel, and I'm left with the limit as n goes to infinity of 2x, actually 2 a sub n plus 1 x over a sub n. Now, the 2 and the x are not dependent on n. So this is going to be 2, the absolute value of x, the limit as n goes to infinity, a sub n plus 1, a sub n. Now, we know that the ratio test will converge if this limit is less than 1. So in other words, 2 the absolute value of x must be less than 1. I can ignore the limit part. And the reason I can ignore the limit part is because I have that part. And so what I know is that 2 times the absolute value of x, and then the limit part is going to be equal to rho, right? So the limit part, n equals limit as n goes to infinity of a sub n plus 1 over a sub n is rho. That's from my ratio test from the last part, 5.5, 5.6. And we know that this happens, this will converge when we're less than or equal to 1. So in other words, my 2, the absolute value of x, is less than 1, which means the absolute value of x is less than 1/2. But this goes back to my definition up here about my r. My absolute value of x minus a has to be greater than r or less than r. So my absolute value of x minus a, well, my a happens to be 0 because my center is 0. This has to mean that my radius of convergence is equal to 1/2. Let's try another one. So for this example, once again, I'm going to do the same thing. I'm going to do the limit as n approaches infinity of the absolute value of a sub n plus 1, negative 1 raised to the n plus 1, x to the n plus 1 over 10 to the n plus 1. Now, if I have a over b divided by c over d, this is a over b multiplied by d over c. Because I would be dividing by a fraction, I'd have a fraction divided by a fraction, that I know that I can write a sub n plus 1 times 1 over a sub n. That's equivalent to a sub n plus 1 over a sub n. And so I can write my a sub n division as the reciprocal multiplier. So then it's going to multiply by 10 to the n over a sub n, negative 1 to the n, x to the n. As before, I'm going to break apart algebraically any of my powers that have the n plus 1 so that I can do some cancellations. All right, so this negative 1 and this negative 1 to the n will cancel. 10 to the n and 10 to the n will cancel. X to the n and x to the n will cancel. I'm left with the absolute value of negative 1, which will be 1. I'm left with x, and I'm left with 10, as well as the a sub n plus 1 and a sub n. So the absolute value of x over 10 times the limit as n goes to infinity of a sub n plus 1 over a sub n. We want this to converge, so the absolute value of x over 10 must be less than 1. So the absolute value of x must be less than 10. So I get a fairly large radius of convergence. So from my 0, my center, my radius is 10 in each direction. Let's do one more of these examples. So the limit as n goes to infinity of n plus 1, x to the n plus 1, e to the n plus 1, multiplied by the reciprocal, so e to the n over n, x to the n. This is the limit as n goes to infinity. N plus 1, well, there's not much we can do about that, but we can write x to the n times x, e to the n times e to the n, x to the n. E to the n's cancel, x to the n's cancel. This x and this e will come out front because it's not dependent on n. So this is equal to the absolute value of x over e, the limit as n goes to infinity of n plus 1 over n. But this is just equal to the absolute value of x over e, the limit as n goes to infinity of 1 plus 1 over n. Now we know as n gets very large, the second term inside the absolute value will go to 0. So this is equal to the absolute value of x over e, which has to be less than 1 for this to converge, which tells me that my r is equal to e. It's my radius of convergence. Up here was my radius of convergence. Take a look at the next two examples. I have two more examples to do. The limit as n goes to infinity of the absolute value of 2 n plus 1 factorial x to the n plus 1 over n plus 1 raised to the 2 n plus 1 multiplied by the reciprocal, so n to the 2n over 2n factorial x to the n. I'm going to have to do some algebraic cleanup. We'll start with this part. So this is 2 to the n plus 2 factorial, which is equal to 2 to the n plus 2, 2 to the n plus 1, 2 to the n factorial. And this is going to be n plus 1 raised to the 2 to the n plus 2, which is 2 to the n. It's going to be n plus 1 raised to the 2 to the n. And then I'm also going to get n plus 1 raised to the 2. Okay, so this is equal to the limit as n approaches infinity of 2 to the n plus 2, 2 to the n plus 1, 2 to the n factorial, x to the n x over n plus 1 raised to the 2n, n plus 1 raised to the 2, multiplied by n to the 2n over 2n factorial x to the n. 2 n factorials, x to the n cancel. Now, anything that is not dependent on n, I will bring out front. So I have the absolute value of x will come out front. Then I have the limit as n goes to infinity. I have 2 to the n plus 2, 2 to the n plus 1, the n plus 1 raised to the 2n, n plus 1 squared, n raised to the 2n. Now I'm going to use my limit laws that says if I have the limit as n goes to infinity of g of x multiplied by f of x, this would be x goes to infinity, not n. This is equal to the limit as x approaches infinity of g of x multiplied by the limit as x goes to infinity of f of x. So this is going to be equal to the absolute value of x, the limit of n goes to infinity. I'm going to isolate this one and this one. And the reason I'm doing that is because they're both raised to the 2n. So this is going to be the absolute value of 2n plus 2, 2n plus 1, over n plus 1, the quantity squared, multiplied by the limit as n goes to infinity of n over n plus 1 raised to the 2n, because they both have the same power. Now, this we know has the same coefficient, because this has the same, or not the same coefficient, this has the same power. When I multiply this out, I'm going to get 4n squared in the numerator as the highest power. When I multiply this out, I'm going to get n squared as the highest power. So then if I divide everything by n squared and take the limit, we know that this part is going to go to 2. This part is going to go to 2. Here is another thing. This should be the absolute value, by the way. Well, it's squared, so this is actually e. It's actually, well, okay, let me do it this way. The limit as n goes to infinity of n over n plus 1 raised to the n, the quantity squared, is equal to the limit as n goes to infinity of n over n plus 1 raised to the n, the quantity squared, because of the limit laws allow me to do that. But this is equal to 1 over e. I believe we proved that in our Calc 1 class? If you didn't, that's okay. Write that down in your notes. That's something that is, quote, known. So then this ends up going to 1 over e squared. So I have the absolute value of x times 4. Not 2, it should be 4 here, because it'll be 2 times 2, which is 4. Coefficients. So 4. And then I have e squared has to be less than 1. So the absolute value of x has to be less than e squared over 4. And that is my radius of convergence, my r. So my r is equal to e squared divided by 4. All right. Let's take a look at my next example. And I'm going to set it up, and then I'm going to give you the answer. The limit as n goes to from 1 to infinity. And I'm going to do the limit, and I wrote summation. So the limit as n goes to infinity of n plus 1 factorial over n raised to the n, oh, these are the n plus 1s, don't forget. So n plus 1 raised to the n plus 1 multiplied by x raised to the n, so that actually needs to go in the numerator. So x raised to the n plus 1 multiplied by absolute value, multiplied by its reciprocal, so it would be n to the n over n factorial over x to the n. And don't forget, the n plus 1 factorial can be wrote as the n plus 1 multiplied by n factorial. So you have some nice cancellations. And just like n plus 1 raised to the n plus 1 can be wrote as n plus 1 raised to the n multiplied by n plus 1. So I'll let you finish that one off, and I'll tell you your radius of convergence for this one. And then we need to go back. We're like, well, I thought we were done. Well, not really. My radius of convergence on this one is e. What I need to do, though, is I need to decide, is it going to go from negative e to e? Is it going to go from negative e to e inclusive? Is it going to go from negative e to e, one inclusive and one not? So we have to determine whether or not we have endpoint inclusions. So I've just done the radiuses of convergence. I haven't actually found the interval of convergence. It didn't ask me for the interval of convergence. It actually only asked me for the radius of convergence, but I want to take the time, since we've already done all this work, to do the interval of convergence as well. The first two examples that I started out with makes no sense to do the interval of convergence, to go more than just the radius, because I don't know what a sub n is. If a sub n is growing, then it's going to converge or diverge. Depends on what else is happening. Same thing here. So I'm not even going to approach these first two ones to talk about the interval of convergence. It only asks for the radius, but I wanted to do the interval of convergence, at least on C. So with the interval of convergence, I know my radius of convergence is e. My a is 0. So my interval of convergence, what I think it might be, is from negative e to e, non-inclusive. Now I have to actually check both endpoints to determine whether or not one or the other or none of them are going to be included in my interval of convergence. The way I do that, so I'm going to do my check here, is x is equal to, we'll start with the positive side. Let's be positive. We're going to let x equal e. So the summation of n equals 1 to infinity of n x to the n over e to the n becomes the summation of n equals 1 to infinity of n e to the n over e to the n, which is going to be the summation of n equals 1 to infinity of n. Now we know this diverges. So that tells me that at least this endpoint is correct. It's non-inclusive. Now I'm going to check the other endpoint. So I'm going to check x is equal to negative e. So I have the summation of n equals 1 to infinity of n x to the n e to the n is going to be equal to the summation, which I went wild and crazy on that. The summation of n equals 1 to infinity of n e, oh wait, it's negative e, negative e raised to the n over e to the n. Algebraically, I'm going to rewrite this as n equals 1 to infinity of n negative 1 to the n e to the n e to the n. Those cancel. So I'm doing the summation of n equals 1 to infinity of negative 1 to the n and n. And we know this also diverges. So my interval of convergence are correct on the non-inclusive. Let's look at another one to see whether or not we have inclusive or not on the endpoints. I'm going to try to find one in which we will maybe include it. Let's look at D here. D, we end up with R is equal to e to the e squared over 4. So what I think my interval of convergence is, since my a is 0, and then remember I know my a is 0 because I don't see here x minus any number raised to the n, it's just x to the n. So I think my interval of convergence is negative e squared over 4 to e squared over 4. That's what I think it might be. So now I have to check each endpoint, so I'm going to check. X, we're going to start with a positive. And so my summation, which started out with, let me scroll out, summation of n equals 1 to infinity of 2 to the n factorial over x to the n raised to the 2n. Okay, so this is the summation of n equals 1 to infinity of 2n factorial e squared over 4 to the n divided by n to the 2n. Okay, so this one isn't as nice. It's not a nice little cancellation like I had before. I wished it did, but it's not going to. So this can be wrote as a summation of n equals 1 to infinity of 2 n factorial e to the 2n over 4n raised to the 2n. And then I'd use the skills that I learned in my chapter 5 to determine whether or not that is inclusive. I'd also check x is equal to negative e squared over 4. So you would have to check both of those to see if they converge to determine whether or not we will turn these into inclusive for the interval or not. Now, we're going to go on to representing a function as a power series. We know that 1 plus x squared x to the third, just by the way we defined it, is going to be equal to this, and it's the geometric series. And I can check it. My a sub 1 is 1. My ratio each time is x. So here is my ratio. My leading coefficient is 1. And then we write it as n because we're going to start our index at 0. That's how we define a geometric series, and that's how we, up above, defined the power series. We know that this geometric series will converge if my r is less than 1. And it converges to my a, my first term, over 1 minus r. That tells me that if x is less than 1, then it will converge if I have 1 over 1 minus x. And that means that I could write this geometric series as this, but as a replacement of 1 over 1 minus x, where x is my r, for any x less than 1. Which means if I see 1 over x minus 1, I can write it as a power series if my x is less than 1. Okay, let's go through this. I hate it when it unlocks my rotation. It's one of those little pet peeves. Okay, given that 1 over 1 minus x is equal to the summation of n equals 0 to infinity of x of n, with a convergence between -1 and 1, find the power series that is centered at x and identify its interval of convergence. So our goal, let me write what my goal is. My goal is to get 1 over 1 minus x. And I know it's going to equal n equals 0 to infinity of x to the n. That's my goal. So I need to make this look like this kind of structure. And because it can be a little muddy, let's rewrite this as, instead of x's, because I've got x's in my rational functions here. Let's just write this as the generic y and then y raised to the n. So basically, I want 1 over 1 plus x squared to have the same structure, to be 1 over 1 minus y. So if I rewrite 1 over 1 plus x squared as 1 over 1 minus a minus x squared, and this now matches this structure, which means that this is going to be equal to the summation of n equals 0 to infinity of negative x squared raised to the n, which is the summation of n equals 0 to infinity of, I'm going to rewrite this as -1 multiplied by x squared raised to the n. So I can write this as -1 to the n, x to the 2n. Now that's the first part. That takes care of writing it as a power series centered at a equals 0. Now I have to find its interval of convergence. So I'm going to do like I did above in my previous examples. I'm going to do the limit as n goes to infinity of the absolute value of -1 raised to the n plus 1, x raised to the 2 n plus 1, divided by -1 raised to the n, x raised to the 2n, which is equal to the limit as n goes to infinity of -1 raised to the n, -1, x raised to the 2n, x squared, over -1 to the n, x raised to the 2n. This cancels to this cancels to this, and I am left with the absolute value of -1 multiplied by x squared times the limit as n goes to infinity of just 1. So this is going to be the absolute value of x squared, which tells me that for this to converge, I need this to be less than 1. So my radius of convergence is going to be equal to 1 if I square root to both sides. Well, can't really square root over inequality, but we're going to go with 1. And so what I think my interval of convergence is between -1 and 1. As before, I do need to check. I would check the endpoints. I would put x is equal to 1 and x is equal to -1 back into my original function. And my original function being this. Well, not my original function, my original series. And check the endpoints. And decide whether or not they're inclusive or not. Let's take a look at my next example. So I have all of these have intervals of convergence at 0. I thought I had one that I didn't. Okay, well that's okay. I meant centers at something other than 0. All right, so again, my goal. 1 over 1 minus y would be equal to the summation of n equals 0 to infinity of x to, or y, excuse me, y to the n. That's my goal. Because we know that's always going to hold true. So let's rewrite this as x squared over 1 minus a minus x squared, which is equal to x squared multiplied by 1 over 1 minus minus x squared, which now has the correct structure. So this will be x squared, the summation of n equals 0 to infinity of negative x squared raised to the n, which we know is x squared, the summation of n equals 0 to infinity of negative 1 to the n, x to the 2n. Now I'm going to do something about this. You're like, why didn't you do something before? Well, I'm going to bring it in now. So this is going to be equal to the summation of n equals 0 to infinity of negative 1 to the n, x to the 2n plus 2. And there it is. I would then do my limit to determine my radius or my interval of convergence, and of course check my endpoints. And you're probably wondering why I just didn't divide everything by x squared. Why did I do this weird shenanigation of leaving this x squared out front and not divide everything by x squared? Well, let's talk about that now. If I started out with x squared over 1 plus x squared, and I divided each term by x squared, I get 1 over, and I get 1 over x squared plus 1, and then you're like, hey, can't we just write this as 1 over 1 minus a minus 1 over x squared? Well, the problem is that for our power series, we need this to be a polynomial. This is not a polynomial if I have negative exponents. If I were to say this is equal to n equals 0 to infinity of the negative 1, and then I end up with x raised to the negative 2n. If I put in 0, okay, that's cool. I get x to the 0. That's not a problem. That's cool. What if I put in 1? Well, now I've got x raised to negative 2. That's not a polynomial. So that's why I did not divide everything right out of the gate by x squared. I just pulled the x squared out front and dealt with it by bringing it back in. Because x squared is not going to be dependent on n. It's a constant. And I also can't divide everything by x squared unless, of course, when I got done in the denominator, I didn't end up with a negative exponent. And I would have ended up with a negative exponent, which makes it a non-polynomial. So my answer then, why didn't I do it? Well, because I can't. And this is my power series. As before, if I wanted to find my interval of convergence, I would have to do the limit as n goes to infinity of the absolute value of negative 1 to the n plus 1, x raised to the 2, n plus 1 plus 2, and then over negative 1 raised to the n, x raised to the 2n plus 2, and I would go from there. Take a look at my last one. As before, I'm going to rewrite x squared over 1 minus 4x squared as x squared 1 over 1 minus 4x squared. Now it's in the structure that I need, so this is going to be x squared, the summation of n equals 0 to infinity, of 4x squared raised to the n. So this is going to be equal to the summation of n equals 0 to infinity of 4 raised to the n, x raised to the 2n. Still have the x squared out front. Now I'm ready to bring in this x squared. And so this is going to be the summation of n equals 0 to infinity of 4 to the n, x to the 2n plus 2. So there's my series. And as before, to find my interval of convergence, I would do the limit as n goes to infinity of the absolute value of 4 raised to the n plus 1, x raised to the 2n plus 1 quantity plus 2 over 4 to the n, x to the 2n, And of course, I would go from there. And that's it. So the big takeaways from this section is that for me to write my rational function as a power series, which then allows me to actually write it as a polynomial, is I have to make it match my goal. So here's my goal. So that's one of the big takeaways. This is for whenever we have a geometric series. This is true for every geometric series that has a r value or y value less than 1. So that's the assumption here. This is always going to hold true. And to find my radius of convergence, I use this limit as n goes to infinity of my x, -1, x to the n. So with my a sub n plus 1 over my a sub n, and that's going to give me my radius of convergence. And then I should check the endpoints. So once I find my radius of convergence, I would check my endpoints to determine if those endpoints are inclusive or not. And the way I would check my endpoints is I would find the appropriate x based on my center and my radius of convergence, and then put that x back into this series and determine if the series itself for that given x will diverge or converge. And that's it for this section. I will do the video for 6.2 sometime in the next couple of days, but here is 6.1.